nanohub.org.
Online simulation and more for nanotechnology.
Hello, everybody. It's my pleasure to introduce today's speaker, Dr. Daniel Wines. Dr. Wines works as a physicist at the National Institute of Standards and Technology within the Materials Measurement Lab. And his research focuses on the integration of first principle computational methods such as DFT and quantum Monte Carlo, and integrating them with machine learning techniques to investigate quantum materials. Dr. Wines is currently a key contributor on the CHIPS metrology project, where he focuses on multiscale modeling and validation of semiconductor materials. In addition to his research, Dr. Wines is actively involved in the development of JARVIS infrastructure at NIST, which provides curated datasets and tools for materials design. And today, Daniel is going to be discussing one of his latest publications, in which he will introduce a platform called ChipsFF, which can help researchers evaluate machine learning force fields across materials and properties. Dr. Wines received both his master's and PhD from the University of Maryland, Baltimore County in 2019 and 2022, and held a postdoctoral fellowship at NIST from 2022 to 2024. And he also has a bachelor's in physics from Fordham. So that being said, please join me in welcoming Dr. Daniel Wines.
So thank you for the introduction, Juan Carlos, and thank you for the NanoHub team and Professor Strachan for the invitation. Very happy to be here. Would love to visit in person at some point. So my name is Daniel Wines, and I'm a scientist at NIST, working as part of the JARVIS infrastructure, like Juan Carlos said. And today I'm going to talk about one of our latest projects for benchmarking these new universal machine learning force fields with a software package that we developed called ChipsFF. So before I get into things, I have to legally read this disclaimer about NIST and the CHIPS metrology program. Apologies for how long it is, but so thank you for the opportunity to speak and present about my research and development effort at NIST to advocate the microelectronics industry. The purpose of this presentation is informational and preliminary only. It is not evaluative with regard to any application or potential applications to the CHIPS incentive program, Department of Commerce, notices of funding opportunities, grant challenges, or any other department programs. It is not part of the formal process of awarding funds. I am not authorized to make any commitments on any issues for the department, including on specific questions on specific applicants. As a funded project team from the CHIPS metrology program, I and other NIST researchers are presenting information about my R&D activities with a broad set of individuals and organizations. Nothing that I discuss should be understood as indicative or conclusive regarding any CHIPS program. Please do not share with me any information that you are required to keep confidential by law, contract, or professional obligation. NIST, CHIPS R&D, and the CHIPS Program Office do not seek and will not accept any material, non-public information outside of a due diligence process, which is separate from this meeting. So hopefully I have more time now to do the rest. Like I said before, our team is working as part of the CHIPS metrology program here at NIST. So JARVIS specifically was awarded a $5.2 million grant over 4 years for a multiscale modeling and validation of semiconductor materials and devices project. So the total CHIPS Act was over $52 billion investment in 2022, signed by President Biden. And our materials modeling infrastructure was highlighted by the strategic opportunities for U.S. semiconductor manufacturing a few years ago. So I just want to introduce some aspects of the project before I get into the real technical details. So our team consists of a very wide range of expertise. We have experts with density functional theory, type binding, atomistic simulations like molecular dynamics. We have TCAD device modeling, machine learning techniques to kind of connect the dots, and we have some experimental validation as well. So hopefully some people here have heard of the JARVIS project. So JARVIS is a collection of databases, tools. We do a lot of outreach. We have a lot of events. So I encourage people to make an account at jarvis.nist.gov. So JARVIS was started in January 2017, led by my colleague, Kamal Chaudhry. Since then, we have over 50 articles published, over 150,000 users worldwide. Our density functional theory database has over 80,000 materials in it with millions of computed properties. So we go sort of beyond the standard information energy bandgas. We look at other interesting properties such as superconducting transition temperature, spin orbit coupling, and so on. So kind of going past the standard. Some of the events that we organize are the Quantum Matters and Material Science Workshop, which occurs in the winter. And we have the Artificial Intelligence for Material Science Workshop, so the AIMS workshop, which Professor Strachan presented at last year. So this year we're having it on July 9th and 10th. So I encourage people to register if they have the ability. So just a little quick demo of what the DFT database looks like. So you go to jarvis.nist.gov/JARVIS-DFT. We have sort of an interactive periodic table view of the different structures that we have in the database, where you can search by chemical formula or ID. You could look at a variety of properties in an interactive view, or you could download the data set in JSON format to use for various machine learning applications and so on. So I just wanted to sort of get a sense of what the interactive view of the data is before we get into the demo of using the data in a different format. Another project ongoing in our group at NIST is the Atomistic Lion graph neural network architecture. So basically a graph neural network based property prediction model developed by Kamal Chaudhry and Brian Nikos, which was extended to be one of the first unified graph neural network force fields, which I'll talk about in a little bit as well. Some of the other projects that we've really gotten into in the CHIPS program are an interface design toolkit called InterMat. So basically, this is a workflow to generate not just standard bulk materials, but interfaces of two materials, calculate properties such as the band offset, different charge transfer, and sort of analyze and benchmark these results with respect to experiment, and train high-level machine learning models to do these band alignment or work of adhesion predictions as well. One other project, we have a type binding code as part of our CHIPS project. It's a predictive type binding model. Some of the features include charge self-consistency, 2 and 3 body terms in the Hamiltonian. And what makes this type binding code unique is that there's full coverage of the entire periodic table trained on massive or fitted to massive DFT data sets of millions of structures. So there's been an extensive DFT database fitting and testing sort of in an active loop, and we get very nice performance for this as well. So a useful tool for extending beyond the scale of DFT. So why am I talking about all these things? So the main motivation of our project is multiscale modeling. And you can see the classic multiscale modeling diagram where we're going from the quantum scale using methods such as density functional theory all the way up to the macro scale. And what in this talk, what I'm particularly focused on is bridging the gap between the quantum scale accuracy and atomistic simulations. And of course, one way to do this is through machine learning methods. So the concept of a universal pre-trained machine learning force field is relatively new. It was started in the group of Xuping Ong a couple of years ago for the graph neural network-based machine learning pre-trained force fields. And there's a lot of different names for them. There's a machine learning, universal pre-trained machine learning force field, machine learning interatomic potential. People are calling them foundation potentials now. So they all mean the same thing. So basically, graph neural network architectures that are trained on massive DFT databases and geometry optimization trajectories, which are hopefully transferable to a wide variety of systems and have comparable accuracy to DFT. So one of the main advantages is they utilize large DFT databases that are existing, so such as data sets like the Materials Project or JARVIS-DFT that encompass all the elements of the periodic table. So they're transferable. You can use them sort of out of the box, kind of like a black box. So no training or DFT generation is required, or training. And you could achieve near DFT accuracy for certain properties, especially for structural relaxations of bulk materials for energy and forces. So some of the disadvantages are most of these, if not all, are trained on ground state bulk structures at 0 Kelvin. There's no defects or interfaces. And also the predictions can be much more expensive than classical force fields, such as something like a reactive force field or something even more simple, like a Leonard-Jones force field, which can scale to maybe hundreds of thousands of atoms pretty well. And also scratch training and fine-tuning these universal foundation potentials can be expensive and difficult. And the performance for properties beyond energy and force are still remaining unclear, which is sort of the point of this work. So within the past 2 years, several of the universal machine learning force field frameworks have been developed. There's a strong interest from industry on this as well. So almost every major company is working on this now. So I'm not going to get super into the different architecture choices. There's certain choices that are made with how these models are trained versus training on forces directly, or computing forces using invariant versus equivariant architectures and the message passing. And it starts to get very technical here. But just the point is, there are several different models, all of varying flavors. Some of these are proprietary. So companies such as Microsoft, Google, Meta, some startup companies like Orbital Materials or Preferred Networks all kind of have a stake in the game of these potentials now. And the degree of how they're handling the open access versus closed access depends on the company. Some are all open access, some have proprietary ones beyond paywalls. So for our interest, we're interested in benchmarking the open access potentials. And which leads me to my next point of sort of these DFT data sets for the machine learning force field training. And for those of you that don't know, it's been an extremely huge year for this field. Just in terms of basically since 2023, but only one or two of these existed, and now we have dozens. And in terms of data sets, there's been a lot of leaps in releasing massive DFT data sets of millions of structures. So before we had sort of working on the level of tens or hundreds of thousands with databases such as JARVIS or the Materials Project. There's also OQMD, other data sets as well. But recently we have the Alexandria data set, which has been released, which has very high quality data of a variety of materials on the order of millions of structures. And we have the Open Materials 2024 OMat24 data set from Meta, which has hundreds of millions of different snapshots of trajectories of molecular dynamics or density functional theory, relaxation. So these have all been very, very useful for the community. I think even since I've made these slides, there's been another data set related to chemistry released by Meta, by the same team. So the OML25 data set, I think it's called. So this is very rapidly evolving. Things are changing by the week. So what I said, in addition to these open access data sets, we have some other data sets like the proprietary ones from Google. So the genome data set and model, which was published in Nature about 2 years ago. We have the MatterSim DFT data set, and also a data set from the Japanese company Preferred Networks. And very recently from Berkeley Lab, we have a very high quality data set that's been released. So basically what they call a foundational potential energy surface data set for materials, encompasses about 400,000 snapshots of very high quality data, which will hopefully be used in future machine learning force field training. So with the onset of all these different data sets, all these different models, benchmarking is becoming very important. And One of the first efforts to actually capture how these potentials are doing on a targeted task was the MatBench discovery framework, which was started about a little less than 2 years ago. So it's a very popular benchmarking platform, especially for the universal machine learning force fields. Some of the focus is on so how energy is captured, things like formation energy. They've added thermal conductivity predictions recently. And they have very large-scale test sets. It's usually a subset of the materials project of about 200,000 or so computations that need to be done for a user to submit their benchmark to here. And this was the snapshot from a few months ago. I'm sure this is already different. It's changing sort of by the week or month. So in addition to the MatBench discovery, at NIST, we've developed the JARVIS-Leaderboard, which is a similar goal. So we have a large-scale benchmarking effort to sort of address some of the other issues in the material science community. So we're very concerned with reproducibility, transparency of data, validation, the fidelity of the data, so sort of what the data versus the metadata might be in a simulation, sort of how we can compare what we get in a model to the ground truth. And we really want synergy of the computational and experimental databases. So we published this paper last year in MPJ Computational Materials. So it's the JARVIS-Leaderboard, large-scale benchmark of materials design methods. And we have an interactive website, so a NIST website, which hosts these benchmarks that are very dynamic. So some of the benchmarks that we host on this website, and you can see a list of all of our collaborators here. If Arun is in the audience, he helped collaborate on this project as well. So we're testing different methodologies such as electronic structure methods. So that's density functional theory, quantum Monte Carlo, GW, various artificial intelligence techniques. So graph neural network based, single property prediction, multi-property prediction, image classification, generative models. We're looking at classical force fields, so classical force fields and machine learning force fields. And we have a small subset devoted to quantum computation algorithms and experimental data as well. So this is an open platform for people to submit their benchmarks to. So for example, if there is a certain target property from DFT and we train an AI model to reproduce that DFT, we can sort of submit everything. We want to submit a script to completely rerun our model and test it, metadata related to the software versions, the hardware versions, any relevant information to reproduce this. And then once it's uploaded to the leaderboard, error metrics can be recorded and then basically tracked over time. So here is just an example of AI formation energy per atom with a variety of different machine learning methods. Some of them are descriptor based, some of them are graph neural network based. And the thing is, as time goes on and these models get better or they're trained on better data, it's important to keep track of this, and we sort of have a record of how we can move forward and push the field in this direction. So here's just another kind of like a zoomed in version, a snapshot. And so far we have over 300 benchmarks, about 2,000 contributions, about 30 contributors, millions of data points. And we're starting to encourage people that when they publish a paper that you don't just have data availability or code availability, but maybe actually have something concrete like a benchmark availability that can be associated with your manuscript and tracked over time as different models are developed. So I want to shift gears and go back to the machine learning interatomic potentials, so the universal potentials, and talk about some of the more recent and focused benchmarking efforts. So with the rapid development of these potentials, it becomes even more relevant to sort of go through the process, test these potentials for certain applications, see how they do, if they can even go beyond bulk material, sort of structural relaxations. So there have been some benchmarking studies related to phonon surfaces, thermal conductivity. So as this is changing by the day, there's more in-depth ones. Like people have looked at combining universal potentials with CalFad-based phase diagrams for alloys, looking at how force constants are changing with different potentials, and so on. So why is benchmarking of universal potentials needed? This can really allow us to make a more informed decision on which potential to use, not just in terms of the accuracy, but of the cost as well. And for people that are familiar with DFT, so there's sort of the Jacob's ladder picture of DFT, where we have different rungs of the ladder. We start with Hartree-Fock, which has no electron correlation, and we go to chemical accuracy, which is sort of the heaven of how accurate a DFT calculation can be. And as we go up the rungs of the ladder, we become more accurate, but of course the cost goes up. And there are certain systematic trends in this ladder that we've discovered over time, such as LDA versus GGA, which could be underbinding or overbinding, or predicting lattice constants that are too big versus too small. So we sort of want to try to understand this for universal machine learning potentials, and it can help us understand the applicability, what accuracy we might need for certain applications, and help us to develop better force fields in the future. So to do this, we developed a infrastructure called the Computational High Performance Infrastructure for Predictive Simulation-based Force Fields, so CHIPS-FF, which is a nod to our CHIPS funding and CHIPS metrology project. And our goal is, let's create a user-friendly, very flexible benchmarking package to test various machine learning force fields for any material. So we added some capabilities that go beyond sort of what we were seeing, like structural relaxation. So we want to go beyond structural relaxation, look at elastic properties, defects, surfaces, material interfaces, phonons, thermal conductivity, molecular dynamics, and have a very easy pipeline to automate the error metrics as we do this. So here's sort of a workflow, and we recently published this paper in ACS Materials Letters earlier in 2025, myself and Kamal Chowdhury, also at NIST. So sort of the workflow, how this works is we have universal potentials, which we connect with the atomic simulation environment, so ASE, and our JARVIS-Tools software. And we have a variety of different properties we can look at. So we can look at optimized structure, bulk modulus, elastic properties, phonons, thermal expansion, thermal conductivity, molecular dynamics. So we can melt or quench structures, look at amorphous materials, look at the vacancy energy, surface energy, and also look at interfaces. So in our case, we can take starting structures from JARVIS-DFT to feed through our pipeline to manipulate them or create different vacancies or surfaces or interfaces or even test on bulk materials. And then we could use the data that we have in our database to compute the error metrics, so MAE or R squared with respect to what we're testing on for these potentials, and then create them into a format that's appropriate for the JARVIS-Leaderboard and automatically upload it. So here's a little bit of a snapshot of our repository, and we'll look more closely in the NanoHub tool of this that myself, Juan Carlos, and Rushik helped to get online a couple of days ago for this workshop. So if you go to github.com/usnistgov/chipsff, you can see more details about this. I encourage people to go check it out, give it a star or a fork if they want. So basically, the way this works is we wanted to sort of model this off of using a regular atomistic software like VAST for Lens, where we have an input file with some designated tasks, parameters to tune, We have an easy-to-use command line interface. We could easily parallelize this for HPC, whether that's on CPU or GPU, where maybe instead of running 1 or 2 examples, we want to submit a calculation for 10,000 materials or 100 different force fields. It's all very doable. We have a couple interactive notebooks on the GitHub page, which are similar to what I'll show in the NanoHub tutorial at the end of this. But here's sort of like a snapshot of what a full input file might look, where we're giving a material ID, we're giving the type of calculator. So in this case, the CHGNet universal potential, where certain files we might need, like chemical potentials, different properties to compute, different relaxation settings or supercell sizes, displacements, and so on. So here's sort of a snapshot of how some of the functions, the main functions that are used, and on the left is sort of how we're loading in the different calculators through ASC. So the way that this is set up makes things very easy to add a new calculator over time. And basically, it really all it takes is 3 or 4 lines of code. So for example, if a new force field is developed tomorrow, I can add 3 or 4 lines of code, update one file, and then test all the materials I want for a new force field. So we've made this pretty robust in terms of that. Same thing with version upgrades. For example, if there's a bug in an existing force field and they have a new version, we could easily update that, run it through the same pipeline, and same thing. So here are the main functions. Like I was saying, we have relaxation for optimizing atomic structures, formation energy calculation, elastic tensors, calculating energy versus volume curves, phonons, defects, phonon 3pi for third order force constants, MD or InterMat simulations for interfaces as well. Another thing we were interested in is looking at the scaling of these different models, and this can be pretty important in terms of deciding which model to use, outweighing accuracy versus scaling. So we actually did the scaling for CPU just because we were interested in seeing how a lot of people don't have access to GPUs, especially in small environments like looking at Google Colab or on your own desktop maybe. So we want to see how do these force fields actually scale with CPU. And we see pretty good scaling with some of the older force fields that are maybe not as accurate, such as the M3GNet MatGL force field. Some of the equivariant force fields like MACE or SevenNet have a little bit higher scaling. The OMat models, which I talked about, so the models that were recently released from Meta, have pretty unfavorable scaling with the system size, but as you'll see in the next few slides, they are the most accurate for a lot of properties. So in our case, instead of benchmarking on an extremely large data set like something from the materials project that MatBench does, we wanted to focus on a small subset of materials and look at more properties rather than just a larger set and look at just force or energy. So we looked at a pretty diverse data set of around 104 materials that are common for semiconductor devices. They have a pretty diverse group of formulas, some metals, some band gaps, some insulators, pretty diverse crystal system. And we have some bulk and some sort of quasi 2D van der Waals materials as well. So we went on to look at a variety of different properties, like I said, and we benchmark with respect to the JARVIS-DFT database. So the JARVIS-DFT database, all of the data is calculated with the OP-B88 van der Waals functional instead of the standard GGA or PBE, which is used in a lot of other databases without a van der Waals correction. And we're seeing that consistently the OMat models and the orb models from orbital materials with and without a van der Waals correction are producing very accurate geometries. ALIGNN force field is doing a good job as well, but it's possibly biased that we're starting with the same structure that we have from JARVIS, which ALIGNN was trained on so it's trained on the van der Waals material and it's predicting van der Waals corrected lattice constants. We have less luck with some of the elastic properties and bulk moduli, which is an indication that some of the out of equilibrium properties or potential energy landscape is not as accurate for some of the models. So we also looked at more complex properties. So we looked at surface energy and vacancy energy. And basically the way we do this is we construct different surfaces with various terminations, and we take an energy difference with respect to the bulk and divide by the cross-sectional area. And we're comparing also data that has been calculated in JARVIS. So we have a large vacancy data set and we have a large surface data set as well for a ground truth comparison of our machine learning force field ASE workflow. And similarly for vacancies, we can look at the difference of the energy of the defect cell. So create a large supercell, remove an atom with respect to the bulk and chemical potential. So we're looking at sort of neutral defects, so no changes of charge states, but currently that's what we're limited by for the machine learning force field frameworks. And we see pretty consistently that ORB and the OMat models are doing a very good job with surfaces and defects. Some of the other equivariant models, such as MACE or SevenNet, also do a good job, as well as the Microsoft MatterSim force field also does a pretty excellent job with vacancy formation energy. So in addition to the open source force fields, recently there's been a force field released by Preferred Networks, so what's called the PFP potential. They have basically taken our code and ran the workflow with their potential. So it's proprietary, it's not open source, and they were able to get very comparable results to some of the best predictions that we've had for surface energy, which was a very nice finding from them that they published in their blog about this. So very interesting. Some of the limitations of the machine learning universal potentials have been for interfaces. So what you see here is we're looking sort of at two different materials, something like aluminum 111, aluminum 203,001. And we want to calculate the work of adhesion between the two materials. And in addition to this, we want to sort of do an XY plane scan of what the energy landscape looks like for minor perturbations of scanning the two materials together. And the XY scan can give us a little bit of an idea of how smooth the potential energy surface might be at the interface. So what we found is that, and like I said before, we were using these machine learning force fields in conjunction with the InterMat package for interface design and generation, which I talked about at the beginning. So we have a pretty seamless interface, no pun intended, between the InterMat software and ChipsFF for calculating these properties as well. And we find that the work of adhesion predictions are pretty poor for the universal machine learning force fields. When we're doing X, Y, or Z scans, there's some variability in what the potential energy surfaces look like or the energy minimums look like. And I think this is a room for these models to grow. So like I was saying before, a lot have not been trained on interface data. And I think that in the future, this might be a good opportunity to sort of fine tune or make the models better. One other interesting finding we found was for phonons. So we calculated the properties of phonons for about 85 of the 100 materials, and sort of seeing how good can we get the force constants and sort of the overall error in the phonon band structure using the finite displacement method. And what we see is that, interestingly, the displacement that you use in the finite displacement method is very important for the accuracy that you get in terms of this. So ideally, you want to use as small of a displacement as possible. You really want to capture the anharmonic phonon modes. But we actually see that when we use high displacements, which we would think would be not realistic or inaccurate, they're giving us sort of a false sense that these models are accurate, especially for the OMat models and the orb version 2 models. And as we decrease the displacement to what really it should be, the error drastically increases. And this signifies that there is some significant noise in the low force regime, and it possibly might be due to how forces are computed. So for these models, the forces are computed by learning them directly and not computed from the energy surface. So it's through something like backpropagation. So this has been a discussion in the community, especially for the folks at Orbital Materials that developed this model. And they've actually released a version 3 of Orb, which I think sort of solves some of this issue. We have not tested it through our pipeline yet, but we plan to do that very soon. So there is a new version of Orb that has been released since then. So we have more consistent phonon predictions through different displacements using some of the other state-of-the-art potentials. Very good results for the MatterSim from Microsoft. One interesting result that we also tested was, can these machine learning force fields, universal potentials, actually be used for creating amorphous structures? So basically melting the structure and then quenching it at room temperature. Can we actually recover the radial distribution function of an amorphous silicon? And we find that they all do a pretty consistent job of doing this. We found the best results for across the board for the many other properties, like we said, for the OMat models, Orb, and MatterSim, and we're comparing directly with ab initio molecular dynamics, which is orders of magnitude more expensive to do this. So I think this is a very good application of using universal machine learning potentials for actually getting a starting structure for something like an amorphous material. It really can cut the computational effort to get towards that goal. And this is we're doing some follow-up work right now, sort of benchmarking this for more and more amorphous materials, looking at other properties such as the density and so on. So keep an eye out for that. We'll probably be working more in that space very soon. So I just want to go over the last little bit of this quickly before we get to the tutorial. So like I said, we were focusing on a smaller data set, but we wanted to test a couple properties automatically with larger data sets. So we looked at the MLearn data set, which consists of a couple hundred binary crystals, looking at the force error. So we have the capability in CHGNet. So if you want to, you could be flexible on what data sets you want to test, whether it's a handful of materials or something like on this slide where we have force error for data sets that were used to train force fields, such as the one for ALIGNN or the one for MagNet or Materials Project, which was used to train MACE or SevenNet and many others. So finally, really the main takeaway here is we have a very dynamic way to keep up-to-date benchmarks now hosted on the JARVIS-Leaderboard. We have sort of a special benchmark here for CHGNet, which consists of all the different models and the different properties. Here's like the Pearson coefficient here. And we can look at the more larger data sets as well, like MLearn, to see the force error of different models. And we plan to continuously change this over time as new models are being developed. Already on my radar is to add Orb version 3 and some of the others. I think there was another model that was recently released by the startup company Radical AI, and other various startups are taking their stab at making very accurate universal potentials that scale very well. So I just want to emphasize that community contributions are very important to projects like this, especially at NIST. We're very focused on open source, and obviously that's the main mission of NanoHub as well. So we've had some really nice contributions actually from some of the developers of these force fields that are working in these companies. So for Orbital Materials, for example, we were able to find a bug in one of the releases of Orb due to this when we looked at our amorphous structures. And then they were able to make the appropriate changes. We updated it, we reran the benchmark, and we got very nice results. So that's the beauty of community contributions, archive, GitHub, and all of these great things. So I just want to end with, we introduced CHIPS-FF, our benchmarking workflow for universal force fields, benchmarked on a small subset of materials for applications in the semiconductor industry, linking this directly to the JARVIS-Leaderboard. We plan to extend this for some more complicated properties like thermal expansion. We want to extend this to alloys. Of course, benchmark this more for amorphous structures. And another thing we're very interested in is benchmarking dislocations as well of materials. So now that some of these force fields have more or less okay scalability, we think that's also a realistic goal for what we can do. And with that, I think I could take a couple questions before we jump into the tutorial. And I'd like to thank everybody for their attention.
Thank you, Daniel. This was a great presentation. All right, so we have a couple of questions here. First question here was about your party plots. So the question is, most of these models are trained against PBE, but here you're comparing with different functionals and calculating error metrics. If the model can only be as good as the underlying functionals, what do the error metrics are trying to tell the audience?
Yeah, I think that's something you have to be careful about, and it's been sort of a debate for a lot of these things. So the flavor of DFT for all of these databases is different, and I think our main goal is not to say like, okay, this is the end-all, be-all metric of something. I think it's more to say we should be flexible in how we benchmark things, and depending on the property, that might change, but we have the capability where you could change the underlying ground truth to something like Alexandria, materials project, even experiment if you have the experimental results as well. And from working in the space for a little while, I honestly think it is maybe not the most productive to chase very small increment differences in MAE. For example, even for most of these properties, van der Waals, DFT, and PBE will give pretty close results depending on what it is. And I think that most of the time, the error of the force field will be within the regime of what the error between those two types of functionals might be. So I think the short answer is we should be careful with how we assess how good or bad a force field is and make informed decisions based on that. See, depending on what this was trained on, what this was compared to, and maybe what is actually reality.
Okay, that makes sense to me. We have a question that is kind of building on that. So when you're mentioning your errors, you were saying that these errors are good or good enough. Can you comment on what you meant by good enough? When is an error good enough for your party plots?
Yeah, that's a good question, and I guess it's very arbitrary. But I mean, I think at the end of the day, we still cannot rely on these models to be the end-all, be-all solution of a problem. I think they could aid in screening. For example, like if you want to calculate a defect energy for a particular system, maybe you relax with the machine learning force field. It gets you closer to the answer, but then you finish it with DFT. And I think when we're getting into small energy differences, like, for example, for surfaces, a surface energy is on the order of, let's say, like 2 joule per meter squared, but we're finding error that's about 2 orders of magnitude lower than that. And same thing, the defect as well. I think that's the best the state of the arts can do that are trained not on surfaces or defects. Of course, we have, I think, I guess stricter error comparisons for things like lattice constants and formation energies. And it gets to a point where the MAEs that people are showing, like, okay, we have an MAE of 0.00 1 or something in the lattice constant 0.005. At that point, I think we're almost in the era of what DFT can even get you. And I think at that point, it's better to kind of just say, okay, all of these models are doing a very good job, which is why I kind of was careful not to just highlight one model that did the best, but sort of highlight multiple green rows of things that are doing very good for a particular test set like that. So I think same thing with the amorphous structures as well. I think once we're getting into sort of these very minor differences, I think it's safe to say that they're all doing a good job.
Okay, that makes sense. We have quite a few more questions, but I think it would be good if we could run through the tutorials for a few minutes, and then we can go back to the questions.
Yeah, sounds good. Yeah, so I don't have a super long tutorial, but I just kind of wanted to give people a sense of how the software works, and feel free to visit the GitHub page, clone it yourself, play around with it if there's new models you want to add, and so on. So yeah, I want to thank Rushik and Juan Carlos again for helping me get this set up. So I think I kind of just have an example of the workflow I was showing where we're going to run a variety of different properties, look at some error metrics with respect to some of the ground truth data that we have imported. So in our case, we're not going to download the whole JARVIS-DFT database or materials project. I just provided some JSON files that have the structures that we're interested in to just sort of read in, get a starting structure, and then compare the properties. But this is a very flexible, arbitrary thing. You could change this comparison or starting point to whatever you might want. So we could start by sort of importing the necessary functions we have, and then we could read in the JSON files of the sort of the demo, DFT, bulk materials, vacancy calculations, and surfaces. So in our case, this test set consisted of over 100 different materials for semiconductor devices. So that's what's in these as well. And we can go ahead and we'll run a sample geometry optimization. So we have a couple different, I guess, environments that can be run here on NanoHub. So we have the CHIPS-FF one, and there's the CHIPS-FF2. So one thing to be careful of is a lot of these machine learning force field, they do not work well together in the same environment. So I know Juan Carlos and Rushik painstakingly tried to get as many to work in each one as possible, and I give them a lot of credit for that because I'm the person that will just make a different Conda environment for each one. But so I appreciate that a lot. So I think this one has Orb, MACE, and ALIGNN. And then the other one has some of the other models like MatterSim and I think CHGNet. Correct me if I'm wrong. But so we can look at a series of different input files for different property predictions that we have. All of these input files are available on the GitHub repository as well. If you go to CHIPS-FF and example inputs, you'll see them all here, and they can all be modified to what you want. So first, let's run a simple geometry optimization using Orb version 2 and MACE, and then apply some isotropic strain, so energy versus volume, and we could do this for something like silicon and gallium arsenide. So this is what the input file looks like. We have the different JARVIS IDs that we want to run. We have the different calculator types, properties that we want. So we want to relax. We want to calculate the EV curve, some of the relaxation settings, and then we could go ahead and run this right here. Hopefully this will take just a sec. So it's loading the local data set, and then it'll go ahead and optimize the geometry of both materials. So you're starting the relaxation with Orb version 2. This should just take a sec or two. Yeah, while this runs, we'll just go through the rest, and I guess afterwards people can play around with it as well. Yeah, so after this runs, there's sort of a series of output files that can be generated. So here we have PNG file of the E versus V curve, also in text format. We have the relaxed structure in POSCAR format, and some of the error metrics as well in JSON and CSV format. So we could plot with orb, what the E versus V looks like, and the bulk modulus of gallium arsenide. It does a very decent job of calculating bulk modulus here. And we can go ahead and calculate the mean absolute error of what these might be. So once that finishes, you'll be able to sort of make a little bit of a parity plot of A, B, and C for the DFT versus the machine learning force field calculated lattice parameters, and it will automatically calculate the constant, the errors in lattice constant for orb and MACE with scikit-learn. So I don't think my plots will appear unless my calculation finishes, but you can see here we have lattice error for orb of 0.012 angstrom for A, B, and C for those two compounds. And for MACE, we have a similar error of 0.015. And of course, you could extend this to a larger scale computation if you want. You can do this for a number of materials or a number of different calculators as well. So what else? We have the input file for a phonon calculation. So this is an example calculation down here. While the other stuff's running, I can go over. So we have example of phonon calculation with orb version 2 using phonopy, using the finite difference method to get the force constants for silicon. And you see here, what we need to do is we need to relax the structure, of course, first, and then run the phonon analysis. So we're doing a 2x2x2 supercell, and we could pick our displacement. I had a discussion about the displacement before of how this can change depending on the force field and how forces are computed. And after this runs, it should only take a couple minutes. So basically, we're calculating the force constants for the different supercells. We have outputs of force constant files that you would normally have in phonopy, which you can do whatever you want with. YAML files of the different band eigenvalues that can also be used for I guess if you wanted to compare the error in the highest frequency or the lowest frequency, that's what a common thing that people have done. And we can go ahead and look at the phonon band structure as well, and density of states from this in a very automated and easy way. So it's generating these plots automatically when you run them. We could also look at some of the other thermal properties, such as the 0-point energy, which could be important in determining the stability of a compound. We could look at the key capacity and the entropy as a function of temperature as well. Yeah, we have a couple other examples here for doing surface and defect calculations. So for surfaces, what we can do is in the input file, we can define sort of what index for the substrate, what index for the surface we want, whether it's 001 or 100. And then we have an automated way to calculate the surface energy. So in the input file, we have computations of the bulk energy and also the surface energy. So there's different, you can adjust the vacuum, you can adjust the indices you want here. So if you see here, the number of layers, if you go to the surface settings, we can say, do we want the volume to be constant or not? The different indices, like I said, for 001, 111, so on. How much vacuum we want to give, 18 angstrom, 20 angstrom, so on. So we could run this and we could do the same thing. And once this finishes on your guys' end, you can plot the parity plots of for orb here. So I'm picking orb just because orb is one of the more favorably scaling force fields that we could test things on. Of course, you could pick whatever force field you want. So we could calculate the MAE of the surface here using orb. So we have an MAE at 0.295 joule per meter squared for 001 silicon. Similarly, we could do this for defects in silicon as well and get our parity plot and vacancy energy. One other simulation we can run is the melting and quenching simulations for amorphous silicon. So what we can do here in the input file is we can define things such as, of course, which ID we want to run it for, our time step, how big of a supercell we want. So we have an 8 angstrom supercell here, the number of steps for the melting, number of steps for the quenching. So we want 6,000 Kelvin, 300 Kelvin. And then we can sort of see in ASE how this is done, where we're melting for a certain amount of time. These are not production level calculations. It's very little quick tests, but in the end, we'll output some things such as the quench structure in Pascal format and the radial distribution function, which you could visualize. And of course, this is not amorphous. There's a lot of sharp peaks here because we only ran the simulation for a couple of time steps. But if you run the simulation out long enough, you will get what you're supposed to get. And the last little thing I want to show you is we have some examples of testing the automated scaling versus the wall time of a copper supercell with various machine learning force fields. And I think this is very important in terms of, like I said, testing which force fields you might want to use, outweighing accuracy versus scalability. So we have like a 1x1x1, 3x3x3, 6x6x6, so on supercell here, using orb and MACE. And we can get a sense of how these scale, looking here. So orb scales much more favorably than MACE here. And you might have a more consistent trend the bigger you go, if you go out to a couple of thousand or 10,000, like I was showing in our paper. But you can kind of get a sense of, if you're whatever system range you want to work in, you can see how each force field will change. So like I said, there are a variety of different force fields in either of those notebooks so I think, yeah. The variety of different notebooks I encourage you guys to check out maybe a little bit after this, once some of the traffic calms down a little bit. So we have Orb, MACE, and ALIGNN-FF in ChipsFF. And then in ChipsFF2, we have MatterSim and CHGNet. And if we have time for maybe a couple questions, I'm happy to take more.
Yeah, we have time for a couple more questions. There's quite a few here, but let me pick a couple of them.
Okay.
So yes, so there's a couple of questions that are asking about system sizes. What are the system sizes that these potentials can handle efficiently? Like, what would be the largest simulation that you can foresee with these potentials?
Yeah, I think that's a huge bottleneck of what's going on right now. So the one thing is the scaling, but another thing is the memory consumption, which is what you're seeing right now. Basically, these consume a lot of memory, and even if you're running on CPU and you have a pretty sizable node with a lot of memory on it, these can still crash or run very slowly for system sizes of maybe over 1,000. I think in the hundreds range, it can handle pretty good, but there have been a lot of very recent efforts I'm seeing from at least, I think, the Cedar group in Berkeley, and some of the startup companies that I was talking about, such as this Radical AI company, is they're getting these force fields to run much more effectively on GPUs now, where I think it's more feasible to run more of a molecular dynamics level calculation of maybe a couple thousand atoms, where I think if you're just running these locally out of the box how they are here, maybe you could handle a little bit more than DFT. It's feeling like it's maybe a DFT or ab initio surrogate as of now. I think we're not quite there with the scaling these up yet. So hopefully with some more recent implementations and some of the new codes, I guess people are switching things from ASE to PyTorch now and such. So I think we'll hopefully be able to scale up and use the same models in a different framework like that.
Okay, that makes sense. There's a couple of questions too on OMat. So one of the audience members is asking, as far as they understand, OMat was a MACE model. Is there a difference between the OMat model and the other MACE models? Is it different training set or architecture?
There's a little. They're a little bit different. So, they're both equivariant neural network potentials. MACE is an architecture that's based off of atomic cluster expansion, and there's different modifications that were made to it after that. I think, OMat is sort of a spin-off of this equivariant dense former model or something like that. So they have a similar architecture, but they're not exactly the same.
All right. And also in OMat, another one of the attendees is asking for your views on how OMat predictions are on interface thermal properties in 2D materials with defects.
Yeah, I
do
think.
You have any comments?
Yeah, I think that we're not quite there with doing super complicated things with these potentials yet. Like there's a lot of work to be done on the data side and probably on the fine tuning side. Interfaces are not super great, but I think the best thing that these potentials could be used for are as a surrogate DFT relaxer for getting accurate energies and geometries. So and that's not saying that we might not get there eventually, but I think, like, for example, if you want to sample a lot of different configurations and get a lot of energies, a lot of structures, this is a good method. It's showing promise for the amorphous materials, which hopefully we'll have more about that soon. Interface-wise, I don't know if we're quite there. I think that there needs to be a larger and accurate interface database that hopefully can be used to train newer models or fine-tune them, which would be good. But of course, getting an interface data set is tricky. I mean, it's very costly with DFT, and there's a lot of assumptions and caveats with that as well. But I think hopefully we will get there. I mean, with the pace that things are moving, I wouldn't be surprised if within a year or so someone did that.
All right. And then I think we have 2 more questions, and then we can be on our way. So one of the attendees is also asking if you know about any ongoing work towards making these types of force fields but reactive, like Reacts-FF, like universal Reacts-FF potentials, basically.
I am not aware of any of work like that, but I think it would be interesting to sort of incorporate machine learning into the fitting of Reacts potentials. I know some of my colleagues, we have discussed this before a little bit, but yeah, that's maybe a little bit out of my domain with Reacts potentials, but I think that, I guess, like, Reacts is reasonably accurate and it can scale much better than this. So I think it would be an interesting route for someone to go, maybe.
So just a comment on our group, we developed a reactive potential for CHNO based on machine learning that actually outperforms the Reacts-FFs that we've been using for 2 decades. So it's challenging, but there's some work, and it'd be nice to extend the work you guys are doing to reactive interatomic potentials for molecular systems.
Yeah, no, that's great, and I think that's definitely an important push, like, in at least scaling up what you can do, because for net, like, obviously there's you can't really go. What's the size limit you can go with Reacts, Professor Strachan? Is it like in the 10,000s, or you can go up to 100,000?
Yeah, no, React scales very well. We've, I don't know the biggest that we've done, but more related to access to large computers than anything else. It scales linearly with system size. So we've run maybe 100 million or 10 million atom simulations with Reacts-FF, and it's more expensive than simpler potentials, but it scales very well. And it is implemented in Cocos for GPUs. So you can actually run big stuff with Reacts.
Yeah, that's great then. Yeah.
With that, thank you to Dr. Wines for that good presentation, and thank you everybody for attending.